So let's do all of that regression analysis now purely using matrices. As I discussed in the other video, I have our data from the age at first word and Giselle score in two different matrices. The X matrix, which will be matrix A on the calculator, is a column of ones and then a column of my X values. And the Y matrix, which will be matrix B on the calculator, is just a vector of all my Y values. And so the first calculation we're going to do is X transpose X inverse X transpose Y. And we're going to store that into matrix C. And X transpose X inverse X transpose Y gives us the estimates of our regression coefficients. 109.87 and negative 1.127. You'll see if you're following along in the PDF document of this problem that those are the same intercept and slope that we arrive at through a variety of methods. Second up is we're going to figure out the residuals, which will be our Y values minus our X values times the coefficients that we just found. And we're going to store those residuals in matrix E because sometimes they're referred to as errors. So those are all of our residuals. We can use the residuals to determine some other things like S squared and S and R squared and R. To find S squared, we're going to do the sum of the squares of the residuals. So I want the determinant of the residuals times themselves. So that's going to be E transpose E. That'll give me the sum of the squares of the residuals. And take the determinant of that, and that's the sum of the squares of the residuals. If I divide that by n minus 2, that will be S squared for regression. And then if I take the square root of that and store that in a variable called S, that'll be my regression standard deviation. Okay, now that we have the residuals, we can also calculate something like R squared. I discuss on the handout, the PDF, several ways to do this, but basically we want to do 1 minus a fraction, and the numerator of the fraction is going to be the sum of the residuals squared, which is just the determinant of E transpose E. And then in the denominator, we need the sum of the squares of how far y is from y bar. And I discuss in the paper that one way of doing that is, this is a little bit cumbersome, but it's cool because it's all matrices. The determinant of y transpose y minus a fraction. The numerator of the fraction is going to be the determinant of J transpose y, and whatever that value of the determinant is, close parentheses there, and square that, and divide by n, which is going to be the determinant of J transpose J. This should give us an R squared value of about 0.41, which we have seen in other ways of doing this regression analysis. We get the same R squared in Excel, we get the same R squared in Desmos, and so on. The last thing is to find our values of t, and the estimates, remember, the estimates of the coefficients are in matrix C. The standard deviations, or actually the variances of those estimates, are in a matrix called the variance covariance matrix. So I saved S earlier, S squared times X transpose X, X transpose X inverse, and I'm going to save that in some other matrix name. I'll call it F. These are the variances of, this is the variance of the estimate of the intercept. This is the variance of the estimate of the slope. And these two numbers, which are identical, are the covariances of the slope and intercept estimates. So that matrix has the variances of our estimates, and if we take the square root of those numbers on the diagonal, that'll be the standard deviations of our estimates, and that will help us turn our estimates into values of t. So I'm going to make a fraction where the top of the fraction is one of my estimates from matrix C, and the denominator is going to be the square root of one of my variances. So of course the square root of a variance, will be the standard deviation. So a value of b divided by the standard deviation of that value of b. So this is the t associated with our intercept. And if we just change a couple numbers here, get a different number off of the coefficient matrix and get a different number off of the diagonal of the variance covariance matrix, that's the t associated with our slope, b subscript 1. And finally, we can find the probabilities of both of those using TCDF on the calculator. TCDF, we're going to go from 2168 to infinity with 19 degrees of freedom. And we're going to multiply whatever that is times 2. And that number is in scientific notation, so that's very small, essentially a p-value of 0. And then we're going to do something similar with the other value, except this time we're going to go from negative infinity to negative 3.6334, still with 19 degrees of freedom. And I forgot to multiply that one by 2. We multiply by 2, and that's our p-value associated with the slope. So basically, everything that is done in regression analysis can be done pretty much completely using matrices.